SwayamPrabha. Digital India. Educated India.
Good morning, students. Today we are going to talk about the crystal structure in terms of a new light which is known as Miller index. So, we will talk about the significance of crystallographic direction and plane, Miller indices particularly, and then we will try to define the linear and planar density in terms of the Miller index. Now, the term Miller index is actually named after a very famous British mineralogist Miller. In around 1839 he coined this term, and this has been used since then to define crystallographic planes in various types of crystals. So, various minerals which come out of crystalline forms, they are also the same indices has been used. So, from there the overall crystal community has taken this particular way of representing the plane and the directions of crystals. Now, what is the significance of these crystallographic direction and the crystallographic plane? Why we are interested about it? The important thing of this crystallographic direction and plane is that if you know the crystallographic directions, then the deformation under loading in the crystallographic directions you will be able to predict, and also you will be able to get the crystalline planes. Now, we will discuss about it later, that there are certain planes, for example, which has the highest densities of atoms. They are very important from the dislocation point of view. It also helps us, once we know that what are these so called crystal planes, it also helps us to predict the modes of material failure, which we will talk about when we will talk about the failure of various types of materials. And also there are other non-mechanical but important material properties like electrical conductivity, thermal conductivity, magnetic property, piezoelectric property. All these properties actually vary in a crystal with the orientation, and hence a quantitative way of defining the crystal direction helps us also to actually make it clear that these properties, what are the values of these properties and how is it varying from one direction to the other direction. So, let us go to the the Miller index. There are a couple of examples. For example, the turbine blades, which are these days this is being developed with the help of single crystals like nickel based single crystal that is used in some of the turbine blades. Now, they can withstand very high temperature due to the absence of grain boundaries. It is because the blades are grown on close packed direction 110 in a FCC structure of nickel. Now, what is this 110 structure? This is what we will be discussing about. A similar couple of other applications like gallium arsenide lasers which is used in CD players, they are grown from gallium arsenide single crystals along 100 direction. And silicon itself, as you know, which is the single most important thing in the MEMS industry, in computer industry, they are grown from single crystal of silicon along 100 direction. So, that the direction plays a very important role in the mechanical and other material properties, and hence we need to define a system of direction, a system of plane. That is the motivation of us for discussing about the Miller index. Now, Miller indices, they are the designation of the planes and directions. Okay. So, the number of indices actually match with the dimension of the lattice or the crystal. For example, if it is a 3D, then it is there are 3 of the indices that are used, H, K, L. And the other important thing here is that if there is a comma between H, K and and L, then that would mean that we are actually referring to a particular point. But if there is no comma, then it would mean that we are actually referring to an individual plane. So, this comma plays a very important role. Now, there are 4 types of actually symbols that are used in the Miller indices. The first one, which is known as the half moon bracket. Okay. So, that is used for denoting the individual planes, like in this case 1 0 0 is an individual plane. What exactly is this plane? We will see it soon. Similarly, if there are other planes like 1 0 0, 1 0 0, 0 1 0, 0 0 1, all of them together we show actually a curly bracket, so that it shows a family of planes. Now, if we want to indicate just a direction, but not the plane, then we use the square bracket, that is the convention. So, individual direction is actually a square bracket with 1 0 0, and when we want to say about a family of directions, then we use this caret bracket, okay, that shows the family of the directions. So, we have to keep this sign convention in our mind, that half moon bracket is for individual plane, family of plane you are going to use the curly brackets. Square bracket is for individual direction, and family of directions you are going to use the caret brackets. With these conventions in mind, let us see that how to find Miller indices of a given plane. Okay. So, here we have a particular lattice structure in which the plane ABC, as you can see here, that the plane ABC with the yellow color, we want to find out what will be the Miller index of the plane. So, what should be the steps that should be involved in it? First of all, choose the origin O in the unit cell, okay, such that plane does not touch the origin. Okay. That is very important. That is why I cannot take any one of these corners, because those corners will be touching if I take them as origin, then the plane will be touching. So, plane can never touch the origin, and the plane should be closest to the origin. That is also another point why between 2 candidate points, say O and this point at the other corner, we have chosen point O, because most of the points are actually closer to this origin O. So, that is how first you choose the origin. Then you mark intercepts from the chosen origin O along x axis A, y axis B and z axis C. Now, take the reciprocal of them, that is 1 over A, 1 over B, 1 over C. After taking the reciprocal, if you find that there are some multiples that are involved in this thing, then you can actually reduce the multiples. This will simplify it. You can also eliminate the fractions by multiplying them suitably if that is needed. And then if there is any negative integer, in this case it is all positive, but if there is any negative integer, then put a bar above the negative integer in the indices. And finally, of course, you are going to indicate a plane, which means you have to place the moon bracket. Okay? That round bracket is that moon bracket around the indices without any commas, because if you put a comma, then it will become a point. So, without any comma, you just do this. That means, in this case, if I follow that notation, so let us say A, B and C in this case are all 1, 1, 1. Their reciprocal is also 1, 1 and 1. Okay, so, there is no question of reduction of multiple or fraction here. So, now we can directly write it with a moon bracket 1, 1, 1 without any comma. So, that is how you can find the Miller index of a given plane in this particular case. Let us discuss about some other cases. For example, the Miller index H, J, K, which are reciprocals of the parameters L, M, N of each of the crystal faces. Okay. So, if you consider the green face, then green face, if you look at the intercept, so the green face has an intercept value which is finite in the x direction, okay, and y and z direction they are infinite. Why? Because this green plane is actually parallel to the yz plane. So, that is why the intercepts are 1, infinity, infinity, their reciprocal is 1, 0, 0, and that is what is the green face. The green face here is 1, 0, 0. Now, if you look at some other face, okay. So, for example, you look at the brown face. The brown face is actually, you can see here that it is parallel to the xy plane. So, in this case it is xy plane, that is why it is 1 over infinity, 1 over infinity for xy, but for z it is unity. So, reciprocal of it is 0, 0, 1. So, that means this brown face has a Miller index of 0, 0, 1. Let us look at the blue face then. The blue face is parallel to what? X and z. So, that is why x is infinity, z is infinity. So, the reciprocal of them is 0, 1, 0. So, then the blue face will have a Miller index of 0, 1, 0. So, all the basic phases of a crystal lattice, thus you can very easily write down what are the Miller indices of them. Now, let us say if this 1, 0, 0, 0, 1, 0, 0, 0, 1s, all these phases you want to put them together, then you have to have a curly bracket and you can write 1, 0, 0, because they qualitatively indicate all the same type of faces. Okay. So, there are family of the faces. So, let us go to the some other problem, a little more complicated. Okay. Suppose we now have a plane which is as has been shown in this particular case. Okay. Now, we have to first choose the origin. Okay. Now, this again the plane cannot touch the origin. So, that means we cannot take any of the vertices as the origin. Okay. We can't choose between O and O prime. Now, O prime is the closest in this case. So, we go for O prime here, and then O prime has the if you look at the O prime's coordinates, then it is 1, 1, 0, because x axis unity and then y axis unity and then z axis 0. So, this is where we are, that is what is our O prime point. Okay. Now, with respect to the O prime point, let us look at the intercepts of the cell. Okay. So, x axis intercept, how much is it? It is actually the x axis direction from O prime, we are going the negative direction this way. So, that is why it is -1 is the intercept. Okay. Y axis, what is the intercept? Here again I am going in the negative y direction and this is -12, and z axis, what is the intercept? This is in the positive direction and this is unity. So, I can write that the intercepts are -1, -12 and 1. Okay. Now, you cannot keep a fraction. So, let us multiply these all these things further. So, okay, now before we do that, of course, we have to find out the reciprocal value of the system. So, if we take the reciprocal, then it is -1, -2 and 1. So, you are that anyway the problem of fraction is not there, because we are taking a reciprocal in this particular case. Okay. Now, we have taken the reciprocals. So, and there is no further reduction possible. So, we can the minus, I already said you have to use a bar. So, you can now write it as 1 bar, 2 bar and 1, that is the Miller index of this particular plane as 1 bar, 2 bar and 1. So, that is how you can take on the basis of intercept the Miller index of a little more complicated case. Okay. Now, let us look at the indices for a given plane. Okay. So, for example, this particular plane that we can see, this plane has a speciality that it cuts two of the reference axes x and y, okay, and intercepts them at A and B. At these points they are intercepting. So, first thing is of course choosing the origin. Now, in this case again we can choose O as the origin, because O is not touching the plane and it is also very close. So, in comparison to the other side we can take O as the origin. Okay. Now, what are the intercepts in this case? Half x direction, y direction 1 and z direction. This whole thing is actually not cutting the z axis, this is z direction, it is infinity. So, what is the reciprocal? 2, 1 and 0. So, the Miller index of this particular plane is 2, 1, 0. Okay. So, this is again another case that we have solved. If suppose we have intercepts which are like fractions, in this particular case the intercepts of the plane, okay, so they are fractions, half, 1/6, half, then the reciprocal will be what? 2, 6, 2. Now, in this case you can reduce it, okay, because you have to try to simplify it as much as possible to keep everything inside the crystal structure. So, by dividing it by 2 you get it as 1, 3, 1. So, then you can write down that this particular plane is 1, 3, 1. Suppose I take some other plane, this particular case for example, okay, where it is minus half, half and infinity. Again I take the reciprocal which is minus 2 to 0 and I can simplify them dividing all of them by 2 first, that means it will become minus 1, 1, 0, and then I can denote it as 1 bar, the negative is denoted as bar. So, 1 bar 1 0, which is the Miller index of this particular plane. So, thus we are trying to establish how under different cases you can consider the Miller index of the system. Now, if there is a the other point is that there is a very simple way in terms of selecting the origin when you have indices with a bar. So, if there is a bar over a number, that means which is a negative number, then the new origin O prime should have a 1 in the same place as the number with a bar. And if there is not a bar over the number, the new origin O prime should have a 0 in the same place as the non-bar number. So, number with bar, replace this by unity, and if no number is there, then replace it by 0. If there is no bar, then replace it by 0. Some examples, suppose you have 0, 1 and 2. Now, there is no bar, that means the new origin to define this can be 0, 0, 0. Suppose you have the indices 0, 1 bar, 1 bar, then the origin will become 0, 1 and 1, because all the bars are substituted as 1 and 1. 1 bar, 2 bar, 2, that means 1 bar is 1, 2 bar is 1 and 2 is 0. Thus, we can select the origin. This is important when if I give you Miller index and then if I tell you that find out the plane, find out the direction, then you need to define first the origin. So, then this is the way we can define the origin of the system. Now, given indices, let us try to draw the plane, okay, the other way round. So far we have seen that if I give you a plane, what is the index? Now, if I give you the index, what is the plane? Okay. So, select the origin at 0, 0, 0, or if there are negative indices, then select the origin at x bar, y bar, z bar, as just now we have discussed. Now, take the reciprocal of the indices and that will give you the intercepts. So, you can take suppose h k l is that indices, then 1 by h, 1 by k, 1 by l will give you the intercept. Mark the intercept along x, y, z axis as ABCs and then draw plane by connecting these intercepts. Suppose I give you the indices as 0, 1, 1, okay, you have to draw the plane. There is no negative number here. So, you can choose the origin as 0, 0, 0. So, I have chosen the origin as 0, 0, 0. Okay. Now, what are the reciprocal values of 0, 1, 1? Okay, that is infinity, 1 and 1. So, already I get an idea that the plane should be such that it will not touch the x axis. Okay. So, it will now let us find out these the intercepts. Okay. So, if we find out the unit cell intercepts in this case, so we get the unit cell intercept values, and then you can draw the planes. So, essentially each one of them will be lines parallel. So, you can see each one of them, they are not actually touching the x axis. Okay. So, they are not intersecting with the x axis. So, then and you know already that the intercepts are 1 and 1. Okay. So, 0, 1, 1, and then you can easily draw the family of lines, and you can easily get the plane that we are talking about, which is nothing but 0, 1, 1. Suppose I give a negative Miller index 1 bar 0, 0. Then what do I have to do? I have to select a origin now such that this 1 bar will be 1, 0 is 0, this is 0. So, that means with respect to my earlier case, I have to shift it now. So, this is what is my new position, where the O prime has this is 1 with respect to the earlier coordinate system, this is 1, then 0 along y and 0 along z. So, this is what is the point O prime, okay, because that is how I have given the comma for them. Now, what is the reciprocal of them? The reciprocal value of 1 bar 0, 0. Okay. So, that if we find it out, that means this is minus 1, 0, 0's reciprocal. So, this is minus 1 as the first reciprocal, then infinity and infinity as the other two. That clearly tells us that since there is it cannot cut either the y or the z axis, that means it has to be parallel to the this particular plane has to be parallel to the yz plane itself. So, that is how, and also we know that it has to be from O prime at the minus 1 direction. So, at this point we draw this parallel plane, and this is the plane that we are talking about, which will have infinite intercept with respect to y prime and z prime, and it is going to only cut this the x axis at a distance of minus 1. So, that is how we show this line, we show this plane from the mirror index of the plane. Now, there are families of planes which are actually equivalent. Okay. So, different planes having same index in their Miller indices, of course, not necessarily in the same order, is actually shown by the family of planes. That means, you use a curly bracket. Okay. You use the curly brackets, and essentially they indicate actually planes which may have same packing density or same environment. Okay. Say for example, if you look at all the edges of the cubic crystal structure. Okay. So, then this edge, the first edge as has been shown 1 0 0, then these 0 1 zeros, these are 0 0 1. Now, if all these edges, vertical edges, this one, okay, this and this. Okay. So, if all these edges I want to put them together collectively, I can call them as the family of 1 0 0, meaning thereby that you can have all the permutations combinations inside. So, that means your curly bracket 1 0 0 can actually generate 3 of the planes, that is 1 0 0 plane and 0 1 0 plane. Whatever are the combinations possible, 0 0 1. Okay. So, that is what we have shown. Suppose we consider this particular plane which contains the diagonal direction. So, this is actually 1 1 0 plane. The other diagonal plane is 1 0 1 and the other one is 0 1 1. Again, the family is called 1 1 0. So, the family is 1 1 0. That means, I can get actually 1 1 0 of course, and then 1 0 1 and 0 1 1. Okay. So, those are the 3 planes that we have shown. Similarly, in the negative direction we do the same thing and get another family of curves. So, that is how the family of curves are actually the family of planes are actually defined with the help of curly bracket. Now, how to find Miller indices of a given direction? Okay. So far we have discussed about the plane. For the direction, how do we do it? That is very simple. Here you again given a direction, first create a new origin O prime at the tail, okay, and then label O prime, okay, and a new axis x prime, y prime, z prime. Then find coordinates from the tail to the head of the direction, okay, and reduce multiples as usual, eliminate fractions and use bar for negative. Finally, you actually place the square bracket. So, in this case this is a square bracket that we are using in order to denote that this is a direction and this is not a plane. Okay. So, in this particular case, for example, for this direction, okay, so we have O prime as the center origin. Okay. From here this is the point which is connected, and then if I try to look at it, that this point how do I reach? I go 1 unit here positive, okay. I go again 1 unit here, but this is negative, and then I go 1 unit here, that is positive. Okay. So, that is why I can write this to be with this square bracket, that 1, then 1 bar for this negative, and then 1. That is how I am denoting Miller index of a direction. Let us practice some more, okay, drawing directions from the indices. Suppose 0, 1, 2 is given to us, and we have to draw the direction. So, we have to select the origin. Select the origin in this case, as there are no negative indices. So, select it as 0, 0, 0. So, I have selected it as 0, 0, 0. Okay. Now, from here reduce indices to keep the direction within unit cell. So, divide this whole thing by 2. So, that means this would become 0, 1, half and 1. Okay. So, now locate from origin 0, 0, 0, okay, x. So, you have to go 0 and then you have to go half. So, x axis 0, y axis half, and then you have to go 1 full unit to reach this particular point. So, once I reach it, I put an arrow, okay, draw direction from tail 0, 0, 0 to the tip, and that is how we are giving the direction corresponding to this Miller index. So, we can read it. If you see a Miller index, you can read what direction we are talking about. Suppose I give a negative 1 now, 1 bar, 2 bar and 2. So, now I have to select the new origin, and we said that if there is a bar, then you put 1, 1, and there is no bar means 0. That is what is my new origin. So, from the old origin, let us first go to x axis 1, okay, and then y axis 1 and z axis 0. This is the new origin. Now, from the new origin, let us try to define this 1 bar, 2 bar, 2. Okay. So, 1 bar, 2 bar, 2 means actually minus 1, minus 2, 2. So, the intercepts will be minus half, minus 1, 1. So, let us try to show where is this minus half, minus 1, 1 is. So, this is where is my new axis now. We have to keep in our mind that this is our new axis system. So, from here I have to choose the particular point from the origin in such a manner that I have to go minus half along the x axis. Okay. So, this way I am going minus half, and then I have to go minus 1 along the y axis, negative minus 1 I am going, and then I am going 1 on the top positive. That is how we are getting this point and join it by arrow. That is how we are specifying the direction corresponding to 1 bar, 2 bar and 2. Now, similar to, just very similar to the other case, unit cell families, which are the equivalent families in this case, they are shown with the help of the caret bracket. Just like we have used curly bracket for the planes, here we are using caret brackets for the family. So, if you are talking about 1 1 1 caret bracket, it means 1 1 1s, 1 bar 1 1s, 1 1 1 bar 1 1 1 bar. These are actually, if you look at it, these are all body diagonals of the system. So, that is what is the equivalent family in this case. Now, there are very similar such families like face diagonals. All face diagonals are shown by 1 1 zeros. Okay. Cube edges, all cube edges are actually shown by 1 0 0. So, these are directions, the family of the directions. So, keep in mind once again, half moon bracket individual plane, okay, and curly bracket family of planes, square bracket individual direction, caret bracket family of directions. So, you have to keep this and practice. What are the other properties of the Miller indices that we can define? Miller indices of equally spaced parallel planes are the same. In fact, that is why we have shown that all the parallel planes can be actually represented with the help of same Miller index itself. Miller index of a plane passing through the origin is actually shown by a Miller index of a plane parallel to it, because it cannot contain the origin. So, it is shown as a plane parallel to it. If two planes having Miller indices as H1 K1 L1 and H2 K2 L2, and they are claimed to be perpendicular to each other. So, that means it is like their dot product H1 H2 plus K1 K2 plus L1 L2 is to be equals to 0. So, that is one condition of two perpendicular planes from the Miller indices, you can say. All members of family of planes or directions are not necessarily parallel to each other. This point you have to keep in your mind. I just going back to once or two slides, look at these face diagonals. Okay. So, they are all belonging to the same family, but they are not parallel to each other. So, that is the point that we are actually telling here. Interplanar spacing is very important one. So, the interplanar spacing is defined in such a manner that this d h k l, okay, that is like the, for a cube, it is cube side length over the square root of h square plus k square plus l square, that is the Miller index. Okay. So, if you know the side length of a cube, then square root of the square of the Miller indices will give you the interplanar spacing. And interplanar angle you can also similarly find out by using this formulation. You can find out what is the interplanar angle. So, you can find out the interplanar spacing and interplanar angle with the help of the Miller index. There are two more important things that you can find out with the help of the Miller index. These are planar density. So, that is number of effective atoms per unit area divided by the area of the plane. Okay. Suppose we are considering planar density of 110 plane in the FCC crystal. Then if you look at the FCC crystal structure, okay, so you see that you have 1/4 into 4 corner atoms, all corner atoms, okay, plus half into 2 side atoms. So, there are 2 side atoms that it is also having half into 2. So, then the total number of effective atoms per unit area. So, that is 2 in this case, and that divided by the total number of effective atoms actually in that sense. Okay. So, you can consider on that area basically total number of effective atoms divided by the area of that plane, and that area of the plane is A times. So, this is A and this side is root 2 A. So, A times root 2 A. So, that is root 2. So, that means it is A 2 over A times root 2 A, that is root 2 by A square. Similarly, if you consider the 111 plane in the FCC crystal, let us look at the 111 plane. Okay. So, that is containing the diagonals. So, here you are having 1/6 of 3 corner atoms, 1/6 of 3 corner, okay, and half of 3 side atoms. So, there are these side atoms there, you are getting half of these 3. So, total you are again going to get a number 2, but the area is different now. What is the area here? Half times base into height, that is if you work it out you will see it will be root 3 A square. So, the total number here is 4 over root 3 A square, and this is actually larger than root 2 over a square. As a result, you can say that 1 1 1 plane, this diagonal plane is actually most densely packed, more densely packed definitely from 1 1 0, and you can check all other planes and you will see this is actually the most densely packed system. Similarly, this you have done for one case, similarly you can do it for the other cases. Now, the linear density also you can find out, in that case it is number of effective atoms in a line and the length of the direction vector. So, in a direction like 1 1 0, you can find out that it will become 2 over root 2a. And in fact, 1 1 0 direction is again one of the most densely packed direction in the FCC lattice. For the BCC also it is similar, that like highest atomic density direction is 1 1 1 and highest atomic density plane is actually 1 1 0. Now, deformation, why this is important, because deformation in metals actually depends on this linear and planar density. Okay, it is like this, that if you have more number of atoms in a particular plane, then it will be much easier to push actually a dislocation over that plane in comparison to any other planes. That is why most of the times the dislocations travel over the highest density plane. Okay, the equivalence is something like, you consider that as if you have a small piece of paper or cloth and you have some balls below that, okay, and you are trying to pull that cloth. Now, the direction where you are getting more number of rollers, it will be much easier to pull that cloth along that direction. So, that is why the slip occurs on most densely packed crystallographic planes and directions, and that is very important for us to know beforehand, because then you know how to actually so to say temper the steel. So, this is where we will stop, and in the next lecture we will talk about crystal defects and its effects like point defects, line defects and plane defects. Now that you know the Miller indices, it will be very easy for us to actually discuss about the defects and its effects. Thank you.